Hi again, everyone. Dr. Tom McNamara back for our course in college algebra. We are continuing the discussion of our last topic for the semester, which is systems of equations. I've got a problem pulled up here for my math lab. Let me make it nice and big so we can see everything. Okay, so it gives us a system of equations, and it says graph the following system and find any solutions. Okay, in a previous video we had solved these systems using the method of substitution. And you can also solve them graphically, okay, as you can guess by the way they ask this question. So we have two equations here. I'm going to graph each equation. So the first equation is 2x minus y equals 2. All right? So to graph that, I'm going to use the line tool here. 2x minus y equals 2. Now, I guess it's easiest for me when I have the equation in slope-intercept form. So I would solve this equation for y. And I would add y to both sides and then subtract the 2. And that gives me 2x minus 2 equals y, or y equals 2x minus 2. So minus 2 is my y-intercept, and the slope is 2. So over 1 and up 2. So that's the graph. Okay, I'll click save. Oh, wait, I want to put the other one in there too, right? And the second equation, of course, is down here. Y equals 5x plus 1. Okay, so the y-intercept is 1. Give me the line tool. The y-intercept is 1, and the slope is 5. Over 1, up 1, 2, 3, 4, 5. All right, so we've got our two equations there. So we'll check answer. Okay, so this is telling me I've got the graphs correct. Now it says, what is the solution to the system? Okay, now we have to think back about what a graph really is. Okay, this first line is the set of all points whose coordinates satisfy the related equation. So this line right here is the set of all points where 2x minus y equals 2. The coordinates of every point on this line satisfies that first equation. The coordinates of every point on this other line satisfies the second equation. So the point where the two graphs intersect, those coordinates, the coordinates of that point, will satisfy both equations. Okay, we can see that point is -1, -4. So the solution is -1, -4. Check answer. Okay, great. So we have a graphical method for solving systems. Or you could say that solving a system tells us something about the graph. Either way. Now, the thing is, if you're going to do this, you have to have a carefully drawn, precise graph. You can't just do some scribbling on a piece of paper with the axes not perpendicular and the tick marks willy-nilly. Okay, you've got to use graph paper and draw your graph with a ruler. Okay, and then you can get the graph here. Now notice there were some other options. It says there are infinitely many solutions. There is no solution. Okay, if we're thinking about lines, and these are both linear equations, so their graphs are going to be lines. If I draw two lines, well, this is one option, the lines intersect. The other option is that the lines are parallel. That would lead us to no solution, okay? So you can have a system with no solution. We call that an inconsistent system. Okay, so this system is consistent and independent, okay? It means the two lines are actually distinct, all right? So a little bit of vocabulary here. A system is consistent or it's inconsistent. Inconsistent means no solution. If a system is consistent, there are two options. You could have exactly one solution, as we have right here, or you could have infinitely many solutions. Okay, we'll talk about that in another video. But the key takeaways here are how to solve a system graphically. Okay, if you have a linear system like this, graph each of the equations. Where do they intersect? That's your solution. Okay, and that vocab. Inconsistent, no solution. Consistent, there exists at least one solution. Okay, and then underneath that, you have independent and dependent. Independent means exactly one solution, which is what we're seeing in this case right here. Okay, consistent, independent. Consistent, dependent would mean the lines are parallel. Let me give you an example of that here. I want to actually go backwards in my set here. Okay, so they have graphed two equations. So we can see the red line, 5x plus y equals -3, and we can see the blue line, 5x plus y equals 5. The lines are parallel. They both have slope -5. The lines are parallel, they don't intersect. There is no point in common. There is no solution to the system. The solution, or the system, is inconsistent, okay? The system has no solution because the lines are parallel, okay? Two ways to say the same thing. All right, and I'm going to skip that part. Yeah, I know. So let's see here. I wanted to show you a system that was dependent. They probably wouldn't ask me to do it graphically, though. Okay, here we go. They actually did ask me to do it graphically. Okay, so first equation, x minus y equals 7. Okay, if I put that in slope-intercept form, it's y equals x minus 7. Y-intercept of -7 over 1, up 1, 2, 3, 4, 5. Oh, no, sorry, over 1, up 1. Oh, I bet if I check answer, it'll give me the right answer. Okay, because the reason is both of these equations actually have the same graph. Take a second and solve each of these equations for y. You solve this one, I would do the same trick, add y and subtract the 7. So y equals x minus 7. Same thing here. Add the y over, subtract the 14. Okay, so that becomes 2x minus 14 equals 2y. Divide everything by 2 to get y by itself. Y equals x minus 7. Okay, these guys both have the same graph. So there are infinitely many solutions. Any solution to the first equation is also going to work in the second equation. So this is an example of a solution or a system of equations that is consistent and dependent. Okay? So consistent and dependent. So now we've seen examples of all three varieties. Okay, we've seen consistent, independent, exactly one solution. We've seen inconsistent, no solutions, the lines are parallel. And we have seen consistent, dependent, where any solution to the first equation is also a solution to the second equation, meaning the lines actually coincide, the graphs are the same. Okay, so just some background for understanding how some of these MyMathLab problems work and understanding the vocabulary. and understanding how to solve systems using the methods of graphing, in addition to the algebraic methods that we've already discussed.